I'm Charlie Dickens, and applied research scientist at Snorkel, and I'm working on natural language processing in general and Gen AI use cases. And more specifically and recently, of course, I'm working on distillation. So we'll hear a lot about that today. And before Snorkel, I was earning my PhD in computer science and engineering at University of California, Santa Cruz. And uh, I worked on neurosymbolic AI and, of course, on natural language processing applications.
Senior Director of Product Marketing here, but hopefully you won't let it fool you. I was an engineer myself and like to think I'm still a developer at heart. My passion at work has generally been around distributed systems and databases. And then over the last few years, as I'm sure many of us have, my interest has pivoted to AI, a little more specifically around large language models and how they're used. So that's enough for me. Why don't we go ahead and jump into it? I'm going to open with a little bit about why we're talking about distillation today, kind of provide some context for it, give you a few examples of where we're seeing this both in academia and in the commercial space. Then I'm going to turn it over to Charlie, who's going to kind of walk us through, a little more of the details around distillation, right? Different approaches, different solutions. And then we will kind of come back around and share with you our approach to distillation and some of the research that we've done. And of course, as John mentioned, we will try to save some time for Q&A at the end as well. So please don't hesitate to start peppering us with questions. We will be sure to get to as many of those as we can at the end. Now, before we get started, for those of you who may be new to Snorkel or joining us for the first time, I just wanted to provide a very brief introduction to Snorkel Flow, as we will touch on it at a couple of points throughout our webinar today. It's an AI data development platform. So what does that mean? In a nutshell, this platform helps enterprises, accelerate and scale data labeling, right? With the ultimate goal of curating very high quality training data. And certainly distillation is kind of one means of that, which we're going to talk about today. But if we think about some of the features involved, some of the mechanics, part of it is streamlining collaboration with SMEs, right? Whether they're doing some manual annotation or they're adding tags and comments, but it's important to get SME input and feedback in this process. Pragmatic data labeling is really the magic, right? Instead of having SMEs spend hours or months, manually labeling everything, we have this notion of labeling functions, which allows us to, label an entire data set at once based on SME logic. There's built-in error analysis tools, LLM evaluation, right? This is all kind of part of an iterative development lifecycle. Then, of course, once you've reached your accuracy requirements, you can train and deploy that model. So this is a complete platform for developing the data that you need to train models, right, to be more accurate and then ultimately deploy those. But that's enough of Snorkel Flow. Let's jump into the primary topic here today, distillation. I wanted to first start with the context, right? I mean, the idea is, this should come as no surprise to anyone, we want fast, accurate responses from our models, and we want to pay as little as possible in inference costs. Whether that means you're paying, by token to a third party who's hosting a model, or you're paying for GPUs if you're self-hosting it. Regardless of the path, we want to have our cake and eat it too. The challenge here is, I'm sure everyone's seen if we're watching the news and seeing new models coming out on a regular basis, is they're getting bigger. They're bigger and bigger, bigger. Certainly that is fantastic in the sense of what they're capable of. The generalization, it's so broad, right? There's so many use cases for LLMs now. And certainly when you look at, few shot or even zero shot prompting, they're getting better and better at it. The challenge is that as those models get bigger, they have to perform exponentially more calculations and require significantly more hardware. The very biggest models aren't even going to fit on a single GPU, no matter how big that GPU is. And when that happens, there's kind of two side effects. One, the obvious one is the cost, right? If you have to invest heavily in GPUs, or you're paying a high fee for millions of tokens, those are going to add up very quickly. The other side effect that sometimes we see, sometimes we don't, is the response latency, right? Smaller models, while less knowledgeable and less capable, can respond very quickly, and we like that. Very large models, especially if they're running on constrained hardware, take longer to respond, and that can be a little bit frustrating. And so the idea is, how do we solve this? How do we have our cake and eat it too? It's really around model compression, right? The idea is no matter how big these models are, how can we shrink them and make them smaller, right? And by doing so, we want to retain as much of the capabilities and the skills and the knowledge that they have, but still kind of reduce that footprint so it's more manageable. There's a handful of techniques for that. We don't have time to go into them today, but things like pruning and quantization in particular are just methods of removing what we believe are the unnecessary or less important parts of the model, right, to get them smaller. However, when we think about foundation models and frontier models, specifically, in this slide, I was thinking about benchmarks. They're very broad, right? From writing code to performing calculus, using APIs of different tools and services. But in practice, depending on what you're trying to do, you might only need one of those skills, right? If I'm building a co-pilot, or an assistant that helps, for example, customer service representatives interact with customers and answer their questions, I probably want those reasoning capabilities, right? I obviously don't need a large language model capable of writing code, right? That's not what I'm trying to accomplish. So then we kind of rethink it a little bit and say, well, we want fast, accurate responses. Of course, we want our low inference cost, but typically in the enterprise space, we also have this notion of task specialization, right? We're not trying to build a generalized model for the world to do ask me anything, right? I'm trying to solve a specific business problem. And you can often pair that with, I have, ideally, a healthy amount of unlabeled data available to me. So if you're checking those two boxes, distillation is the recommended approach. And that, of course, is the topic today. So we're going to kind of dive deeper into that now. But, you know, when done successfully, we get both of these things, right? We have fast responses, we have low inference cost. And while we haven't retained 100% of the knowledge of the model, we have retained the task-specific capabilities, right? So the knowledge and skills that are necessary to solve our problem, we've retained those. Before I turn it over to Charlie, I wanted to highlight, just two places where we've seen this in practice. One of the earliest examples was Stanford's Alpaca. So essentially, they took the latest GPT-3 model that was available, and they generated, you can see 52,000 QA pairs, right? So kind of using it for self-instruct, generating this training data. Then they took those QA pairs and they used it to train a Llama 7B model. What's fascinating about this and impactful is you see there on the left, less than 2 months and less than $600 was spent. But when they were finished, they ended up with a model that was comparable to GPT 3.5. So again, they have a smaller model. It's going to have lower inference cost, but it's meeting our accuracy and latency requirements. Fast forward a little bit, and NVIDIA just published a research paper not too long ago. I'm not going to do it justice here, so I encourage everyone to check it out. But the summary is this notion of, instead of pre-training a variety of models in a family, from very small to very big, what if we simply started by, pre-training our large model? In this case, it's Nemotron 15B, and then chose to both prune and then distill the knowledge from the teacher to create a smaller one. And that's Minitron 8B. And then, of course, they did it again, right? We're going to prune Minitron 8B down into Minitron 4B, and then we will use distillation to retrain that model. The key takeaway here is that red line in the graph. So you can see the original Nemotron 8B, cost to train, and then kind of on the left side, the accuracy, what is it, maybe, 55% in this benchmark. A similar size model generated through distillation ended up being significantly less expensive to train and delivered much higher accuracy. Even that Minitron 4B model was delivering higher accuracy than the original Nemotron 8B model. So this is an example kind of more recently in the commercial space where people are actively applying distillation. One side note here, both of these examples, of course, are more in that generalized space. But as we kind of get through the conversation here with Charlie, we are going to circle back to examples where we're now focusing on more specialized tasks and why distillation is the best method to achieve it. So with that said, I'm going to turn it over to you, Charlie.
I'm Charlie Dickens, and I'm an applied research scientist at Snorkel. And I'm working on natural language processing and Gen AI, and of course, distillation, which is what we're here to talk about today. And it's a super exciting field to be in, as I'm sure you are all aware. And in this part of the slide deck, I'm going to try to give us a common mental model, a common way to think about knowledge distillation. Shane teed me up perfectly. There's strong motivation for distillation, which is we want fast and accurate responses for specialized tasks. So we can really minimize costs, give the best user experience for our applications. And we'll see some example applications and specific ways to use distillation right now. But let's start with a working definition of knowledge distillation more specifically. So this is introducing some common lingo that's used in research and practice for knowledge distillation, which I break down here in two steps: extraction and transfer. So first, we're extracting knowledge from a generalist model. This is going to be a large language model, hundreds of billions of parameters. This is our teacher commonly. And we're transferring this knowledge to a specialized model. This is most commonly going to be a small model, hundreds of millions of parameters, or even less. And we're thinking of a specialized task or a specialized domain for this student model is what it's called. So the extraction process takes as input seed knowledge, and this is something that's going to elicit the knowledge we want out of our teacher. We'll see hard examples of this. And of course, it takes the teacher. And the output of the knowledge extraction process is going to be used in knowledge transfer. And we're going to see different forms of what can be extracted from the teacher. I think that's actually one of the most interesting directions of research now in the era of large language models, what type of knowledge we can extract from our teacher. In the knowledge transfer process, we're going to take that knowledge we extracted and potentially ground truth. This is actually optional, so we can learn only from our teacher if we want to do so. So let's dive in to knowledge extraction. I'm going to break this down into a few steps. First, we identify the target skills and domains we are targeting from our teacher. What do we want to retain? What skills do we want to retain from our teacher? Classification, information extraction, summarization, and also like the domain we're going to be applying our student model in. Second, after we identify target skills, we need to curate seed knowledge. So seed knowledge could be in-domain examples. This is probably the most common case. In-domain examples of input that the student and teacher might see in our task we have in mind. We'll also see prompt templates. These are very useful for seed knowledge to elicit information or supervision from the teacher specific for our use case. And finally, with those two things, we can start to generate teacher knowledge. We need to think about what we specifically want to extract from our teacher. This could be labels, synthetic data, hidden representations, and feedback. And this is a foreshadow into the slides that I'll go into next. I'm going to cover in detail what I mean by labels, synthetic data, hidden representations, and feedback. Let's start with teacher labeling. This is probably the um, first thing you could try for distillation. And this is what was covered in the seminal work from Jeffrey Hinton back in 2015 and distilling knowledge from large networks. I might have missed that title, but it's close. And the idea is we're using a teacher to create supervision for a student. So the teacher is curating a training data set for a student. In this example, we're looking at health insurance question answering. So the teacher's provided the input, why is the hospital billing me? And the teacher outputs, you've only paid $100 of your $750 deductible. That input and output pair are provided to the student for supervision, and altogether, this pipeline looks like this. The teacher labels are provided to instantiate a loss function that we minimize using familiar algorithms like backpropagation and gradient descent. So this is actually one of the more surprising outcomes of distillation, and I think I want to spend some time clarifying what's going on here. The idea is we're using the teacher to create labels, and these labels could actually be soft labels, and this expresses uncertainty and knowledge embedded in the teacher. And this has actually been shown to be better than teaching on the ground truth, even if you have it. So if you additionally add some uncertainty coming from the teacher, for instance, this is better than training just on the ground truth. And this is kind of counterintuitive because you're evaluating on the ground truth. So why would you expect to actually improve using just teacher labels? And the idea is the teacher model has some inductive bias that you can leverage. And this inductive bias today is coming from extremely large models, hundreds of billions of parameters. And we can leverage this inductive bias to improve student performances, improve smaller model performances. But of course, we've moved on from just teacher labeling because labels don't capture all of the rich knowledge that a teacher might have, especially in large language models. So the first improvement is using hidden representations rather than just the output of the teacher model. So this time I'm looking at text classification is our task. And the seed knowledge is, again, in domain examples, but also a classification prompt. So this could be a few shot or zero shot chain of thought classification prompt provided to the teacher. For example, help the user classify prompts into 1 to 5 categories with some category definitions. And finally, the prompt input, what is the capital of France? And the teacher responds, informational. But we also have hidden representations in the earlier layers of our teacher that we could leverage. And both the output or the label provided for this text classification problem and the intermediate layers are provided to the student. And you could still think of this as curating a training data set for the student using a teacher model. But now our training data set not only includes labels, but also hidden representations that we can map to the student architecture. So the hidden representations express a more nuanced understanding of the task and data than just the final output, and we can leverage this. And this has been actually especially useful in areas like self-distillation and computer vision architectures. Actually find this to be very valuable information. But we are still requiring a large and good representative source of unlabeled data. That was true for both teacher labeling and hidden representation. So to overcome this weakness, we need the next form of knowledge distillation I'll present, which is distillation via synthetic data. So now we're actually expanding the student training data set, expanding the inputs as well as the outputs that the student model has access to for learning. Again, we're looking at text classification for the target skills. And seed knowledge this time is a data generation prompt rather than just a classification prompt. So it could be something like an informational prompt is and then add your definition there, generate 10 examples of informational prompts. You could also leverage in-domain examples if you have some informational prompts in mind already. The teacher model, since it's a generative model, can generate representative examples of this class that you provide to the student. The student takes as input the classification prompt we saw from the earlier example, and the output should be the informational prompt that was used to generate this data. The pipeline altogether looks something like this. The teacher model generates labels and synthetic input data for the student to train on. So this looks slightly different from teacher labeling and hidden representations. But again, we still get to use backpropagation and gradient descent after the teacher model curates the training data set for the student. So with synthetic data approaches, we can leverage the generation capabilities of teachers to overcome a lack of specialized data for your tasks that you have in mind. But there could be a misalignment of synthetic and real world data. So this is where after the curation of the training data set, you need to drill in and understand deeply your data that you're training your student with. You need to make sure you're not amplifying biases present in the teacher. So this is an ongoing and really interesting direction of research because you have control over the distribution of your training data set by using a generative model as your teacher. And finally, I want to cover knowledge distillation by feedback. So now the teacher provides feedback on the student generations. And this pipeline looks a lot like reinforcement learning from human feedback, if you've seen that. I'm using health insurance question answering as the target skill for this example. And the seed knowledge for the teacher this time is a feedback prompt. So this could be something like a rubric, a grading rubric for generations from the student model. So just walking through this example, we're going to prompt the student potentially multiple times with the same input to generate multiple outputs. These multiple outputs are provided to the teacher, which ranks the responses in this example. And these ranked responses are used to train a reward model. So this is where distillation happens. The teacher model has preference knowledge that is elicited using the feedback prompt, and we can distill its preference knowledge into a reward model, which could then train a student in a scalable way, because providing multiple on large data sets rankings becomes expensive. So altogether, this pipeline looks like so. We have a source of unlabeled data, which we provide to a student to create generations. Generations are provided to a teacher, which gives feedback. And feedback is used to train a reward model, which we can train with or use to train a student using algorithms like proximal policy optimization. And if we actually want to skip the reward model, there's also direct preference optimization techniques. And this is recent reinforcement learning research that is very exciting to create this even as pipeline even more simple. The strengths of this approach is that feedback prompts can be specialized with subject matter expert input. So you can create a rubric to define what you value in generations. And this automates the preference feedback process. And by distilling the preference knowledge in a teacher language model into a scalable, fast reward model, you could make alignment of the student something more scalable. The risk here is, of course, like commonly found in distillation techniques, is the risk of reinforcing teacher biases. And my answer to this is data-centric, of course. We need to look at both the data that is being used as seed knowledge to elicit knowledge from the teacher, as well as the curated data set that is being used for the student model training. Okay. So that was a lot. I'm going to quickly summarize what we just saw. Knowledge distillation is extracting and transferring, extracting task-specific and domain knowledge from a generalist teacher model and transferring it to a specialized student. There's 3 steps to knowledge extraction: identifying target skills in the domain, curating seed knowledge, and generating knowledge. We covered multiple ways to generate knowledge. teacher labeling, hidden representations, synthetic data, and feedback. And I'm not going to claim this is exhaustive, but I think this is a pretty good representation of what you will see in practice as well as in research right now. So I think we're ready now for the Snorkel AI approach, which is data-centric knowledge distillation. And these are advanced techniques for distillation. So distillation step by step is a recent paper that came out of the great minds at Snorkel as well as Google research teams. And we are using language model rationales that are elicited using step-by-step chain of thought reasoning prompts. So you might recognize the step-by-step term from another paper, which showed that large language models are good zero-shot reasoners. So you can elicit step-by-step reasoning by using a let's think step-by-step style prompt for the teacher model. When you use this type of prompt, the teacher model will generate a rationale as well as a response that you can use to transfer or train a student model. Specifically in distillation step by step, this is done via a multitask framework. And if you do something like this, you're going to be able to be more data efficient. So you require a smaller labeled/unlabeled data source. In fact, in the paper, they showed an exciting result, which was a student 770 million parameter T5 model, which is small by today's standards, is able to outperform a few shot 540 billion parameter Palm model with less training data. So let's break step by step down, step by step. First, knowledge extraction is done via, as I stated, chain of thought, few shot chain of thought prompting. So for this example, we're looking at multiple choice question answering, and the teacher model has provided an example rationale label pair, which elicits a rationale label pair output that is used to train a student model. This knowledge is transferred to the student model via multitask learning. And for distillation step by step, multitask refers to the two tasks of the student model. The student model has to both predict the correct label or the label coming from the teacher, as well as match the rationale generated by the teacher. So that's two tasks. And these two tasks are indicated by a label or rationale token. This are special tokens provided to the small specialized language model. So with this approach, we see super exciting results. First, comparing distillation step by step by vanilla standard task distillation teacher labeling, this is what we saw, versus distillation step by step on 4 data sets here: natural language inference, common sense question answering, and arithmetic math problems. And we see across the board in all these tasks, all these data sets, distillation step by step is more data efficient. In fact, it outperforms standard task distillation with less training set size. So you can see on ANLI, for example, with only 12.5% of the training data set size, distillation step by step is able to outperform standard task distillation with the full training data set. So you can get more out of your data using this approach. And this pattern is repeated with fine tuning. So this is in contrast to distillation. So now you have ground truth labels rather than just teacher labels. So this is a slightly different setting, but this is also important to point out. If you have ground truth labels, it's still valuable to use distillation step by step. Leverage rationales from your teacher. This is similar to the idea of leveraging uncertainty, but now instead of uncertainty quantifications from the teacher, it's rationales, reasoning steps that you can transfer to your student. The next set of results is showing that student models are able to outperform standard distillation and a large few shot chain of thought teacher model, PALM 540 billion parameter model. So this shows that you can actually outperform a large language model that is being served via few-shot chain of thought reasoning for your specialized task using a small T5 model that is distilled. So this would cut costs and actually outperform the alternative. And this is repeated for fine-tuning as well. And now I want to share with you exciting recent developments at Snorkel on taxonomy development at scale. So this is taxonomy generation and distillation. The motivation behind this work is taxonomies, or systems of classifications of your data, enable multiple things, including important fine-grained error analyses and dataset curations and dataset analysis, just understanding your data. But building quality taxonomies is demanding and costly. So building rich taxonomies, you might not have a taxonomy in mind, but you do want to have fine-grained understandings of the performance of your models, or just a fine-grained understanding of data for your use case. So our method is to develop a subject matter in the loop workflow for enhanced taxonomy ideation, refinement, and distillation. Distillation is going to make this whole thing scalable. So let's see this. The subject matter expert is going to provide some seed knowledge. This could come in the form of just a description in natural language of the type of data in your problem. It could be, for example, you're seeing prompts, and you just say prompts are something provided to a language model to elicit information. This is provided to a language model, which begins the taxonomy development process or refinement process. So it refines that initial idea, proposes taxonomies starting from that initial seed knowledge provided by the subject matter expert. The subject matter expert reviews this, modifies it, and this is a loop that will develop a richer and richer taxonomy for your data. Data is provided to the language model to provide in-domain examples, so you can think this as additional source or seed knowledge if you have it. It's not required, but it can help make sure that the representative or the taxonomies are representative of real-world data. But as you can imagine, classifying text against a taxonomy, this is a hierarchical structure, is going to be expensive if you use zero-shot hierarchical text classification with a strong large language model via zero-shot or few-shot prompting. But we want to do something like this because it avoids costly manual annotation. So we generated this taxonomy and we want to label data with it. It's very expensive to hand it off to subject matter experts to click through your data and classify it against that generated taxonomy. We don't want to spend subject matter expert time doing that. Instead, we want to do something programmatically. We want to use our teacher model to do this for us. And for that, we need zero-shot classification capabilities. But using frontier models is also slow and expensive. For example, classifications of 65,000 roughly instructions from the ultra feedback data set with a large language model via zero-shot chain of thought prompting, and using synchronous requests, which are required for hierarchical text classification since there's a dependency on the classifications using the structure of this taxonomy. This can take days and cost over $1,000. And if this is an iterative process, you want to label your data and then improve taxonomies, this is going to take too long. We don't want to spend days developing taxonomies. We want to spend minutes, hours. So our proposal is to leverage distillation, of course. And we're going to distill the zero-shot hierarchical text classification capabilities of large language models into a network of small models that are going to be able to maintain the level of accuracy we desire, but also lower inference costs down to, for this example, minutes instead of days. And we can do this on a laptop if you use correct or smaller architectures for classification. So this is super exciting work, ongoing research, and we see the value in this for customers. And this is actually available now in Snorkel Flow extensions. So it's ready for customers to use. And this is part of our new effort at Snorkel to deliver cutting edge research and accelerate AI developments through Snorkel Flow extensions. I'm going to hand it back to Shane for some more case studies and finally close of this distillation talk.
So we're going to wrap up here with just a quick run through a case study and a project that we did here at Snorkel, kind of a recap or takeaways of distillation, and then hopefully we'll have some time to answer some more questions. While Charlie was walking us through the process, I saw a lot of great questions coming in, so please feel free to keep adding those, and we'll do our best to get to them here shortly. I thought this was a great one to share with everyone. The idea here is there's a repository of legal contracts, and it's called LEDGAR. And the task was to essentially classify legal provisions within these contracts. So what you see on the right, B, C, D, E, F, those are provisions. And then, the bold words, headings, applicable law, right? Those are the classifications of those contracts. In total, there was 100 different classes. And we grabbed a data set of 80,000 of these provisions, and you can kind of see how we split it across train and test. In terms of data labeling, you kind of looked at it and realized that, in any other context, we would require a contract lawyer, right? And at the time, it was about $75, $74 an hour to have a contract lawyer review these provisions and manually label them, which of course we want to do. But as a baseline, we can look at, well, how would we approach this if we want to fine tune GPT-3? And there's kind of three different data set sizes there in terms of ground truth, right? So at the first one, our contract lawyer would label 100 provisions, right? All the way to the end, labeling 1,000 provisions. So the result here is, say, a little over $7,400, right? Spent on having an expert, label ground truth data for us. And then that kind of resulted in 72.5% accuracy, right? So I'd say that's very good. We have good accuracy. In the inference costs, those are essentially to run the test and kind of validate it. Then we kind of thought, is there a better way to approach this, particularly with distillation in mind? I'm not going to read all these here verbatim for you, but the idea is we can look at multiple foundation or frontier models as teachers. So we kind of bring in our contract provisions, and then for each of these contract provisions, we can ask each of these foundation models to classify it for us, right? Here's the provision. Here's a list of classes. Please choose the correct one. Of course, for each of those provisions, we're going to have labels from multiple teachers. They may all agree, they may conflict, but part of what happens within Snorkel Flow is actually that process of building an internal model which is able to choose the correct label. But even after doing that, we realized that there was still some edge cases where even these foundation models were not getting the class right. So we did a little bit of more work. We actually introduced another approach with TF-IDF that when certain rare words were used, we would actually use that to generate the label, right? And it would be more accurate than these foundation models. But using all of these signals to kind of generate these labels, we then curated a new training data set and then fine-tuned a Roberta model, right? A much, much, much smaller model compared to GPT-3. And if we kind of look at the results, in this process, of course, there's some cost to have these teachers label our training data, right? GPT-3 was the most, but we use kind of a handful of models available to us with kind of varying degrees of accuracy. What you see on the right, those first two rows, that is the accuracy of our fine-tuned Roberta model using just the labels from that specific teacher. So if we use labels solely from GPT-3 to kind of distill its knowledge into our smaller model, we had 65% accuracy. If we use Snorkel, which is better able to capture labels from multiple teachers and choose the correct ones, we're able to actually increase quite a bit to 71.3% accuracy. What's notable here, before I move to the next slide, though, is the inference cost was almost negligible, right? This is a very small model that we can run on our own AWS infrastructure, and it's borderline free at this point. And so if we look at it in summary, these two different approaches. First is standard fine tuning on GPT-3. Our example, say $7,500 to build this fine-tuned model. It's going to be, roughly $175 for every 10,000 tokens, roughly 72.5% accuracy. This Roberta model, which we trained through distillation, barely 100 million tokens, right? A small fraction of the size, was, less than a third of the cost, right? The inference cost, virtually go away. And the accuracy was nearly identical, right? They're both at about 72% accuracy. So if we circle back around, to my very first slide, we want fast, accurate responses and to pay the lowest inference cost possible. Distillation is the right approach, especially when we're talking about specialized tasks and unlabeled data, which is represented by this case study where it was very specific. We needed to classify provisions in legal documents, and we had 80,000, unlabeled documents available to us. In that scenario, distillation gave us the model with all the attributes and properties and benefits they're looking for. So some final takeaways here before we kind of, gear up for a Q&A. One reminder is that performance is, always limited by the teacher, right? So it's probably going to be fairly rare that you're going to, build a student that surpasses the teacher. And so it is important to understand the capabilities of the teacher and even other teachers, right? So if you're looking for, reasoning, or I'm looking for translation or classification, especially if it's within particular domains, LLM evaluations can help you select the best teacher for that task. The other thing that I thought was worth kind of noting is this emergence of Llama 3.1, right? This family of models is pretty amazing. I believe the largest one, 405B, completely rivals GTP 4.0, right? In a number of benchmarks. And it's open source, which kind of opens up the door to a lot more possibilities. One thing that, I can't remember if we discussed earlier, but when you're looking at closed models as teachers, you most certainly won't have access to the sources of knowledge that Charlie mentioned earlier, right? You can't get at the features or the logits or the probability distributions. You might be limited to the hard labels, right? Or the actual responses. So having very sophisticated open models kind of changes the game, in that sense. We kind of have new competitive teachers that are open and a lot more possibilities introduced to us. The second one is the importance of data development, right? Or the quality of your training data. And curation is an important part of that, right? As we're doing distillation, and I think Charlie mentioned this a few times, there is that seed data which we use to elicit, additional knowledge from the teacher model. So if there's something wrong with that seed data, right, or it's coming up short, or it's not quite aligned with the task at hand, that's going to have a downstream impact on the knowledge that's being extracted and then used to train your student. And then certainly, while we would like to have, a healthy amount of unlabeled data available to us, it's certainly not a requirement, right? We can always look at synthetic data generation through the examples that Charlie showed us. So really important to keep in mind, selecting the right teacher and using evaluation to do that. And curating the training data that you also use for your student, right? It's not necessarily just take it from a teacher element and drop it into a student. We saw that with the example I was walking you through, where it turns out that when we're classifying these legal provisions, there were some edge cases that these foundation models were not getting right, right? So it was important to have someone like an SME actually take a look and review it, and then, kind of provide their feedback and logic to how we can correct that so that we can actually have the right labels generated. And then kind of bring it back full circle with Snorkel Flow. Hopefully, the connection was a little bit clearer throughout the webinar. But the great thing about it is we can pump a significant amount of unlabeled data into Snorkel Flow, right? 80,000 in our case study here isn't even necessarily a lot. And then Snorkel Flow actually has capabilities within it to label that data for you, right? Whether it is prompting an external foundation model or maybe even a hosted open model that you have available, such as Llama, adding those labels. There are abilities to add additional functions in logic, right, for generating labels. SMEs can kind of collaborate with data scientists to further curate that training data. So kind of as a follow-up to the previous slide, we're not necessarily using it as is. We use LLMs and other features to give us a head start, but then we have to kind of curate that until it reaches the quality level needed to result in a highly accurate model downstream. And then finally, you can use Snorkel Flow to ultimately kick off training and deployment in the platform of your choice, whether that's AWS SageMaker or Databricks Mosaic AI, or Azure ML services. But Snorkel Flow kind of serves as your central point here for performing these tasks and helping with distillation. So time for Q&A, but quick reminder for everyone before we do, Snorkel is having our first ever user conference coming up next month. So we'll have a 2-day conference in New York City. Day 1 is going to be hands-on workshops. So if what you saw today was fascinating, this is a great way to actually get hands-on. We're going to be performing workshops to cover things like building classification models, fine-tuning RAG pipelines, LLM evaluation. So a great way to experience Snorkel Flow, kind of put some of this to work. And then day 2 will be a number of sessions, both from Snorkel AI researchers and others, such as Charlie. We're going to talk about these things, as well as some of our customers are going to talk about the AI work that they're performing and how they're going about it. Get to the good stuff here. I know you had some great questions, so I'm going to turn it over to John.
We have actually 2 questions from Mitesh. The first is smaller generalist models like GPT-4o mini, which can also be fine-tuned, are super cheap and accurate and might be a better solution than an SLM when fine-tuned and hosted on a GPU, cost and performance-wise. How does SLM compare to models like these?
Yeah, that's a great question because GPT-4o mini is different. It's changing the game. But I would still advocate for trying using, for instance, this is going to be use case by use case. For example, text classification, try using a sentence or document embedding and a small prediction head on top of it, because that's going to be cheaper than GPT-4o mini still. And if you're working with GPT-4o mini through a API, it's certainly going to be faster if you can use in-house compute for that. So I think GPT-4o mini is great as a small generalist model, but there's still room, and I don't see it going anywhere for a long time, for specialized models for specific tasks. If you have a very specialized task, you can probably distill it down into an even smaller model that's going to be cheaper to serve and faster.
Awesome. Mitesh also asks, what kind of training data size is preferred for the distillation process?
That's a open question. There's a lot of research going on right now about how much compute you need to get the performance you want. And really, that just means there's no good rule of thumb. So it's going to be, again, use case by use case. If you don't have a lot of data, starting with a pre-trained model is going to be useful, and then fine-tuning it. So that's kind of what the implication of fine-tuning is. That means you have a pre-trained model and you're going to fine-tune it for a specific task. That usually, if you have a pre-trained model, you aren't starting from scratch. That's just the implication of fine-tuning, to clarify that. And that will help. And There's different techniques. We saw multiple today for being more data efficient. So distillation step by step, you might only need a few hundred examples to get the performance you want, but you're going to have to try. So I would recommend that trying, iterating, and improving your models with Snorkel Flow.
This is a question from Francisco. Asks, distillation is a fine-tuning method and not fine-tuning itself. So I think it's just around kind of definitionally
Yeah.
what is distillation.
Yeah, I peeked at that one. That's why I started touching on it. So distillation is implying you're learning from a teacher model. So you're getting labels or information for training a student. Fine-tuning implies you have a pre-trained model that you're fine-tuning for specific tasks. So that means the model went through a pre-training phase on general tasks like next token prediction, and then you're specializing it for a specific task. That's fine-tuning. And you might be using ground truth human manually annotated data, whereas distillation is generally, it could be training a model from scratch with teacher labels. There's obviously overlap between these two methods. You could be distilling from a pre-trained model for a specific task, and you could be mixing in ground truth. But these mental models, like distillation, when we're talking about it, just means student, teacher, extraction, transfer, and fine-tuning is pre-training and then fine-tuning for a specific task.
Awesome, thank you. And Gerald asked, and I think this came up during Shane's segment, when you said it took less than 2 months to distill, this depends on the compute used, correct? So how much of what compute was used for 2 months of work?
Yeah, this was for Alpaca. So the first point, I believe the team spent about 5 weeks on the project. So this is not specifically time training the models, but start and end from a project of, you know what, I have an idea. I think we can create, a smaller model comparable with GPT-3 to how do we do it? How do we execute on it? How do we deliver our results? Roughly 5 weeks. In terms of the training itself, the initial run was, I believe, 3 hours on 8 A100s. And I think it came in at under $100, right, for the initial fine tuning. So very quick all around, but hopefully that provides a little bit more clarity on those numbers.
We have a question on how and which models should be picked as LLM and SLM when we plan to distill knowledge. For example, can I pick GPT-4 as LLM and BERT_small as SLM for distillation? I think this one could span both Charlie and Shane, because I think there's some considerations, both technical as well as relative to terms of use on some of the models. So I'll let maybe Charlie go first if you have an answer, and then Shane, if you have a thought, you can chime in.
Sure. Yeah, this question comes up all the time. So you have a problem and you need to start picking architectures you want to try for distillation. So an architecture for your teacher and an architecture for your student. And my approach is looking at benchmark performances and their correlation with the task I have in mind. How did embeddings from one model perform on this specific task? And I pick the highest ones. And also there's some consideration for, of course, is this model open source? Because if it is, it's going to ultimately be useful for other types of knowledge extraction that we were hinting at before. And I'm not going to be rate limited working through this model through an API, things like that. So there's practical considerations as well as like benchmark performances and things like BERT. Like encoder models, there's not going to be masked attention. So there's considerations like that for encoder versus decoder. And if you're getting like a representation of the text as a whole rather than as a sequence, sometimes like BERT encodings might be better as like sentence embeddings for specific tasks. But again, I would refer to benchmarks for that. There's, sorry, I can't give a direct answer, but there's just a lot of things to consider. There's a lot of architectures right now, and this is, yeah. Exciting field to be in, but yeah, hope that
That's one
helps.
place where, the Snorkel team can also help. If you have a project, you can always reach out on our website, and we'd love to learn about your project. We can provide perspective on the specifics. So we're always happy to dive in with folks on projects, and you can always reach us at snorkel.ai and also at info@snorkel.ai. And Shane, I don't know if you had anything to add to that one. Otherwise, we'll.
Yeah, I think the only thing I would add is that, I think it can be a little bit challenged because there's a number of puzzle pieces that you're aligning. So, and Charlie, help me out here if I stray too far, but I think one of the things that would come to mind is it's probably easier if you stick to teachers and students with similar or the same models. It wouldn't necessarily say it's impossible, but depending on your approach, if you want to do, for example, transfer of hidden representations that you had mentioned before, that I imagine that's going to be a little bit more challenging if you're picking wildly different student and teacher architectures in an attempt to do that. Versus it may not be as much of a concern if you actually want to go on the hard labels, right? You just want the text coming out and to use that for training.
Yeah, all these things feed back into each other. Hidden representations, yeah, you're going to need to align those hidden representations in some way, so you should have similar architectures. If you're only using labels, like you mentioned, like architectures can be pretty significantly different. And I would start to consider costs of the student and expected performance over architecture.
And we have a question from Mo. Would soft weak labels from teacher models essentially act as label smoothing for the student model training?
Yeah, you could think of using soft labels as a form of regularization, like label smoothing. But I think, using the logits or probabilities from the output of the teacher is starting to peek into the dark knowledge embedded in the teacher. And there might be more than just normalizing regularizing towards like a uniform distribution like soft labels do. And I think using probabilities and uncertainty quantifications is moving towards a richer understanding of text that's available in the teacher, whereas using label smoothing is more like a prior on the model that you're regularizing with. So there's probably get performance gains in a similar way, but you can use both to get best of both worlds, I think.
Awesome. Well, I see we're here at the top of the hour.
Yeah.
So again, everyone, thank you so much for joining us. We do have an upcoming webinar that's going to dive deep on data labeling, and that's going to come up here later in September. You can check that out at snorkel.ai/events. Thank you, everyone. We look forward to seeing you at either a virtual event or hopefully at SnorkelCon in New York City. And thanks, gentlemen, for today's great presentation.
Thanks, everyone.